Hello everyone. Before we get into the actual gameplay, I would like to give a brief explanation of what I will be showing you. I am not a teacher by any means, so I will be attaching links to videos from people who are much more qualified to explain the topics mentioned here for those who are interested. My main focus is just to give you some context about what is being done. So, first of all, let's talk about number bases. Number bases are different ways of representing values. The most common one is the decimal system, where digits range from 0 to 9 and are always multiplied by powers of 10. Let's take the number 32 as an example. In decimal, this value is 3 times 10 raised to the power of 1 plus 2 times 10 raised to the power of 0. For those who don't know, any number raised to the power of 0 equals 1. The binary system works similarly but uses only the digits 0 and 1, and each of these digits is multiplied by powers of 2. Let's use the number 32 again. Its binary representation is 10000 because we have 1 times 2 raised to the power of 5, followed by 0 times 2 raised to the power of 4, and so on until 0. The hexadecimal system, on the other hand, is base 16, where digits range from 0 to 15, represented as 0 to f. The number 32 in decimal, for example, is represented as 20 in hexadecimal, meaning 2 times 16 raised to the power of 1 plus 0 times 16 raised to the power of 0. The hexadecimal base is widely used because it reduces the number of digits needed to represent large values, making it more compact and easier to read than raw binary. In digital systems, electronic circuits work with two states, on and off. That is why we use the binary system, as it directly represents these two states using only the numbers 0 and 1. This characteristic makes the binary system fundamental to computing and digital electronics. Now that you have an idea about binary and hexadecimal bases, let's talk about diodes. These components are made of two different semiconductor materials. One has free electrons, while the other has a lack of electrons. This difference allows electrical current to flow in only one direction. In the case of LEDs, light-emitting diodes, when current flows correctly through the component, part of the electron's energy is converted into visible light, which makes the LED glow. It is important to remember that the current must always flow from the anode to the cathode, never the other way around. Now that we understand diodes, let's talk about 7-segment displays. These components consist of 7 LEDs arranged in the shape of the number 8. Each of these LEDs can be turned on or off individually to form different numbers and some letters. For example, to display the number 8, all segments are lit. To display the number 1, only the right side segments are turned on. These displays can be common cathode or common anode, which affects how they are connected in the circuit and determines which states turn the LEDs on. In digital systems, we always have only two possible states, on and off, or 1 and 0. This shows how the binary system and Boolean logic are fundamental to representing digital systems. In this next slide, we see the names of each segment of the display, as well as the representations of all hexadecimal digits, ranging from 0 to 15. Our project will be a binary to hexadecimal converter. This is because, in computing, logic and calculations are performed in binary, but representing numbers in this base can be lengthy and impractical. For example, the number 32 in binary is 10000, which takes up much more space than its hexadecimal version. A group of 4 binary digits can be represented by just one hexadecimal digit, making it easier to read and interpret values. For our system, we will have 4 inputs, each representing a binary digit. The most significant bit will be called E3, and the least significant bit will be called E0. The outputs will be the segments of our display. A value of 1 means the segment will be on, and a value of 0 means it will be off. For example, if we look at the number 0 in the binary input and analyze the output, we will see that on the display, all LEDs will be lit except for the G segment, which is the only one with a 0 value in our table. Having noted this, let's now pay attention to the output columns individually. Notice that each output must have a specific behavior for each possible combination of the 4 inputs. To determine the logical expression that tells us how each output should behave, we must use the Karnaugh Map. The Karnaugh Map helps us organize outputs in a table as a function of inputs, allowing us to group values equal to 1 into sets of powers of 2. The goal is to group as many ones as possible to simplify the corresponding logical expression. This is important because by reducing the complexity of the expression, we decrease the number of logic gates and electronic components needed to implement the circuit. For those studying, it is interesting to build the map manually, but since I have already studied it, I used an online calculator to obtain the logical expressions. The link to the calculator is in the description. The only difference is that in this calculator, the matrix is transposed compared to mine, and the inputs have different names, which I noted in the upper corner of the slide. The screenshot shows the E output. With these expressions in hand, we can create the logic circuits that will ensure our system works properly. So here is the logic circuit in KiCad for every output and the relation between the input and output. Next, I will show you how this circuit was implemented in Crumb. Moving to Crumb, we can see here our 4 keys and 4 LEDs to represent our binary number, our display, and between this huge mess of wires we have our ICs with the logic gates of NOT, and OR. And as you can see, for the binary number I input, my display will show its hexadecimal form. Just to end, I wanted to briefly show you the tools available in Crumb and how it feels to use it.